accepted, challenge accepted. The attitude is always challenge accepted. Challenge accepted, challenge accepted. The attitude is always challenge accepted.
It is time to take us deep into the world of Linux and security.
Our next speaker is an engineering manager at Cloudflare and is here to blow your mind about the kernel keystore.
Ignat Korchagin has worked on various security projects, from ethical hacking to cryptography and low-level programming.
He started as a security researcher with the Ukrainian government's communication services. And if you have a Samsung mobile device, its security probably relies on Ignat's contributions.
Now it is time to welcome him on our stage. Please make some noise for Ignat Korchagin!
Thank you. Let me see if I can make it work. Cool. Hey everyone, thank you for coming. My name is Ignat, and today we're going to talk about Linux kernel keystore. Thanks for actually welcoming me here in Bulgaria, especially today. The weather is so nice because I'm from UK, and the past 2 days I was very confused with all this heat and sun, and today really feels like home. Thank you very much. So, before we begin, how many of you actually knew that Linux had a keystore? Oh, one couple of hands. Okay, maybe you'll learn something new today. Yeah, a little bit about myself. Anyone here doesn't know what Cloudflare does? So I don't have to introduce it. Who doesn't know Cloudflare? No hands. Good. Okay, I'll skip that part. So I work on Linux at Cloudflare. I'm passionate about system security and performance, and I enjoy low-level programming like Linux kernel, device drivers, bootloaders, and other stuff written in unsafe programming languages. So, yeah. Speaking of unsafe programming languages, the whole talk about, to introduce you to the concept of the key store and why it's useful, let's talk about application keys in memory, right? Keys or secrets or password, and here you could see that even NSA recently recommended companies not to use unsafe programming languages in production. So unfortunately, I'm now a fugitive and I'm not allowed to program anymore, but it is. And to talk about applications keys in memory, let's revise the operating system address space concept. So in a normal operating system, and even inferior operating systems like macOS and Windows, you have the concept of an address space. So yeah, you have several applications running, and you have a multitasking operating system. But what exactly is running in your memory? So first, it's kind of like your main logic, the business logic you program into your application, right? Then you might be using some kind of a shell libraries with code. Then you have your application data, which is kind of global variables, local variables. And specifically for local variables, you also have the call stack, right? And again, you're running it on some operating system. So underneath, there is a kernel. So when you usually talk about low-level programming, you know there is the above is user space, the below is kernel space, right? And in kernel space memory, you have the code, which implements the kernel. You also have static and dynamic variables, drivers, and stacks. So the whole idea of the operating system address space isolation is within your application, anything can access anything. I can address any memory in my application, and the same actually happens inside the kernel. So I can address anything. If I'm inside the kernel, I can address anything inside the kernel. But I cannot address a memory of another process, so I cannot easily poke what other processes has in memory, neither code nor data. And the same thing, you cannot poke inside the kernel. You have to use a well-defined interface to communicate with the kernel. Clear? So yeah, let's actually now zoom in into the data section of your process. So what kind of data is there? So first of all, it can be your internal state, your variables, right? Your data. If your application processes some user input, so you can have like user and customer data in your memory, right? And the most importantly, what you can have in your memory is cryptographic keys. So if you're running a web server, your private key for your web server is most likely in your application address space. And the problem with within the process, so if suddenly either your code or the libraries you're using becomes compromised, well, because I can address anything within my process, my whole data becomes kind of compromised, right? But not all the data is created equal. Well, if your application internal state is compromised, it's kind of like, it depends on what you're doing. It can be good or bad, but for example, it can lead to further compromise if you can influence with the data the control flow of your application, right? If you suddenly leak customer data, this is much worse, right? Who here knows about Equifax and what happened to them? Yeah, some hands. So yeah, they leak customer data, a lot of fines and problems, but it's not the complete end of the world, like companies survived. But if you leak your cryptographic key, the one which like if I leak a cryptographic key for google.com, it's a game over, right? And this is what happened when Heartbleed happened in 2014, is it, right? So how can you leak the key? So for example, let's say you have some stuff in the memory, and normally your application, and then next to it you can have a cryptographic key, depending how your application gets executed. And normally your application is supposed to access only stuff. But what happened within Heartbleed, so like the attackers could influence your application to read past the buffer boundaries and actually access and leak the cryptographic key, right? So, well, if your code has arbitrary remote code execution, there is nothing to discuss. If an attacker can control your code, they can read any data that your process is processing, so it's a game over. And this was the example of the log4shell vulnerability, right? Here is a simple self-contained C program. Don't focus too much on it, but you can later copy-paste it and compile yourself. But it has a bug, right? It has two functions, encrypt function and log function. But in the log function, I forgot to initialize the array, message array. And technically, if you compile that application, you would see that it inadvertently leaks the secret in my encrypt function. So what happens here is like this is a process stack. So I have my main code running, then my main code calls encrypt or decrypt function, and that function gets the key from somewhere and puts it on the stack, right? When the decrypt function finishes, so the key is left on the stack, and then I call the log function, and the log function kind of accesses the same memory on the stack. And this is where if the log function itself has a bug, it can leak the key accidentally. So that's why if you ever talk to compliance, they always say, oh, well, you should always zero out memory for your keys if you're not using them. But it's very hard to do in high-level languages, like with garbage collection, like Go or Java, for example. Another way you could leak your keys is, well, if you have a bug and your application crashes, so some operating system create a thing for debugging called a core dump, right? And the core dump is basically a snapshot of your process address memory space, and it can contain cryptographic keys. So, well, we can say, OK, let's just fix all the bug, right? So, but it's not very practical. The bugs will always happen. So what the industry does, it tries to take the advantage of the operating system address space isolation, and they realize you cannot protect all your data from these leaks, but you can try to at least protect cryptographic keys, because this is the most valuable data you can have, right? And what they do is they create another process and basically move the cryptographic keys there, right? And implement some very simple logic and a well-defined interface between two processes. So now we call that an agent model. So now the advantage of it that you have now two processes, main and helper agent. The main is usually networking facing the rich project, but the helper only manages your cryptographic keys. It's kind of like a software token. Who here uses SSH? Yeah, have you used an SSH agent? Yeah, so SSH agent is a primary example why you need this, right? So you put your keys in a different process, and if SSH itself has a bug, it's not at least exploitable from the network to leak your private key, right? Yeah, think of an agent as a software security key. So you hide the key from your main logic to another process. Of course, this model has some drawbacks because now, instead of developing one application, you need to develop two applications. You need to design this well-defined interface. You need to add communication support, and you have to think about, is it a Unix socket, like shared memory, whatever, and also probably you need to think how to authenticate the main process from the agent, because I don't want any process on the system talking to my agent and using my keys, right? So this brings us to Linux kernel key retention service. This is the official name of the technology, but I call it like a Linux kernel key store. And the idea here is simple. So you take this agent model, and instead of the agent, you replace it with a kernel, right? And your well-defined interface is already there. It's called system calls. So this is exactly what Linux kernel key retention service is. It can store your cryptographic keys as kernel objects. It was initially designed to share keys with the kernel itself. So for example, if you run disk encryption, you need to hand over the disk decryption key to the kernel so the kernel can decrypt your disk. But it was later extended to user space application to manage their keys and secrets. And the nice thing about storing a key as a kernel object, it's also now has a proper access control bits, so you can have a really fine-grained control who can access and use that key. And surprisingly, for a Linux kernel feature, it has very good documentation, so you can go and read about it. Within the Linux kernel key store, there are two basic types of objects. It's like key rings. Key rings may contain either key rings, and key rings may contain keys. So the key ring is like a collection of keys, and the key is actually the key itself. And you may see that it's very similar to a file system structure, except that, for example, a key is a file and key ring is a directory, right? But the difference is key can be in several key rings at the same time, unlike a file, which can be only in one place, usually. So yeah, keys are actually contain the cryptographic material or a secret you want to let the kernel to store for you. You can read and write the key and use the key to perform cryptographic transformations. They have different types, and we will go into them later. And it's similar to file on the file system, where a key ring, it can contain links to other keys, and it can be explicit or implicit. And it's like a directory. But the nice property about the keyring, it determines the life cycle of the key, which I will be showing further. So here is a simple example of a key store use. So we have two users on my dev machine, which actually do not share any groups. So what Alice can do here, Alice can create a secret, some password like hunter2, and store it inside the kernel. And basically, all the keys and key rings are represented in the kernel by a unique serial number, so she gets the serial number back. Now, Alice wants to share that secret with Bob, right? So what Bob can do, Bob can create a new key ring, call it from others, so other users can share keys with Bob. And Bob can change the access control permissions on that key ring to allow other users to write there, to put keys inside. Then Alice can actually move her key from her key ring to Bob's key ring, and we can now see that Alice doesn't have the key anymore. And Bob can actually now read this secret. So a simple secret sharing mechanism where two users share the password without any shared credentials, like groups. Yeah, and Bob now has the key in his possession. So this was an example of explicit keyring, but now what about implicit keyring? So there are process keyrings which are implicit, which are always there for you for and private to your process. So any process on Linux can store keys in their process keyrings. There is user keyrings, which are dedicated to lifetime of a user. And there are a thing called persistent keyrings, which are more complicated, I won't explain them in detail in this presentation. But the whole idea behind the keyring, if a key is linked to keyring, the keyring defines the life cycle of that key. So here is a simple example. I'm actually SSHing to my dev machine here. So I'm storing a secret to my session keyring, right? And I can see that I have the secret, right? So the last line is my secret. Here it is. Now what I'm going to do in another terminal, I'm going to attach a BPF probe to a function in the kernel which is responsible for securely destroying a key. And now in the first terminal, what I just do, I just log out of my SSH session. So what happens here is because my key was only attached to my session keyring, when I logged out, the system destroyed the session keyring and therefore destroyed my key. So as you see in the second terminal, my key was now securely destroyed. And if I relog in again, I don't have the key anymore, and I can also see that the serial number for the session key is different because the system destroyed it and recreated a new one. So this is how it's very handy to use keyrings to securely destroy keys, because basically, even if your application suddenly crashes, if you store keys in your process keyring, the process keyring will get destroyed and your keys will get securely destroyed from the system. So the whole takeaway here is that if you select the appropriate keyring type, you can ensure that keys will be securely destroyed when not needed. Now about the key types. So there are, like in previous example, we saw the simplest key type is the user key. So you have some secret, you can put it in the kernel, and either you or any other process who has appropriate access permission can read that secret. There is a variation of that called logon key, so you can put it into the kernel, but you can never read it back. And why it's useful, it was actually created to support in-kernel encryption system like disk encryption or encrypt.fs. So you only need to share the key with the kernel, but you never have to read it back. And if you're running a modern Linux distribution with disk encryption, which you should, you will notice that your encryption keys are stored as logon keys inside the kernel. There is also asymmetric key types. So imagine you have an RSA key, and you can put it in the kernel. So, and another process, or you yourself, you don't have to read it back, but you can ask the kernel to perform cryptographic operations like decryption or signing, which is very handy for web servers. You can store your TLS private key inside the kernel, and you can do like TLS sessions without having to have the key in your address memory space. So like if you do that, for example, the heartbleed will never be a problem for you anymore. So yeah, this is a simple example. I skip it through, so you can just generate a private key, put it inside the kernel, and then ask the kernel to sign something with it, and then you can basically verify that you get a valid signature. So I want to mention, and I'll repeat the link later, like we even wrote a small proof of concept patch for OpenSSH to actually store your SSH keys inside the Linux kernel key store. So now you don't have to run an SSH agent. You can put the keys inside the kernel key store and SSH to your remote systems without having to run a dedicated agent process, which is very handy. But key store is a nice thing, but let's look at high-level examples of what you can do that. And the big question is, how can we provision application keys without cryptographic material ever being exposed to user space applications? Because in previous example, we still see that at some point, the bytes, the secret, are still exposed in the applications because application has to put it inside the kernel. So how can we do that the application never sees the plaintext cryptographic material? So there is a concept called encrypted keys. So imagine the kernel key store already has some key. What you can do is you can take an encrypted key, encrypted blob, and try to put it inside the kernel. And when you put it inside, the kernel will automatically decrypt that key. So like in kernel address space, the key is in plain text, but when you try to read it back, it will be automatically encrypted. So, well, in user space, you will never get a plain text key in your address space. Of course, you may notice that this problem is a chicken and egg problem. So how do I put the wrapping key, right, without exposing it? So another type you can do is like a TPM. Who here knows what a TPM is? Yeah, it's a security chip which is present on most laptops and servers. So you can actually like create a wrapped key wrapped to your TPM, and you can put it inside the kernel, and the kernel will use the TPM to automatically unwrap it. And when you read it back, it will be encrypted to the TPM again. Well, TPMs are very slow and sometimes not reliable devices, so you don't want to poke them too much for many keys. So most of the time, you would want some kind of combined schema. So for example, you have your cloud or on-premise KMS or HSM service, which wants to distribute keys to your application. So what it does, it creates a root key for all the other keys, and it provisions you to production as a TPM encrypted key. It's called a trusted key. So now the kernel has a trusted key, and all the other keys are distributed as encrypted keys with this root key. So you basically poke the TPM only once for the root keys, and all other keys are encrypted with software, and you can distribute many keys from your HSM service to production machines without invoking TPMs too much. There are some problems of that. Even though we achieved our goal that application never see plain text cryptographic material in their process address space, but still applications are somehow responsible to communicate with your remote service. Who here uses Vault? Some people, or Amazon KMS, right? So like, you need to code stuff into your application to connect there, right? And like, you as an application developer do not want that. So you need to know how to reach your centralized key management system, how to communicate with it, and basically you have little administrative control of the created kernel objects. Yeah, and KMS needs to somehow authenticate every application on your production to actually give it the proper keys. So Linux kernel keystore has a solution for that as well. So far, we have been using under the hood the add key system call, and the add key system call basically has the semantic of an application says, hey, I have this cryptographic material, create a kernel keystore object for me. It can be encrypted or plain text, but the application is responsible for giving that byte block. But there is another system call called request key, where an application is not responsible anymore for providing this material. It just pokes your kernel and say, hey, kernel, give me my key. And the kernel now is responsible to actually understand where to get the key from. And of course, everyone's setup is different, and you don't know, like when, your kernel doesn't know where to get your keys from because someone uses Vault, someone uses AWS, right? So what you do is, the way how it works is, let's say an application requests some key, and usually it just needs to give an identifier, which is a free-form string. So it calls the request key. So what the kernel does, it creates a small placeholder object inside the kernel, and then it calls out to a so-called helper process on your system, and it's located as being request key. And that process is actually, you can configure it to kind of understand your infrastructure. So you can configure it to understand where to fetch particular keys from. So you can write plugins to that process and say, like, depending on the identifier, you can either fetch keys from a local HSM, from your cloud, or somewhere else, right? So like, for example, if you want to request a key from the cloud KMS, it will be configured to reach your cloud key management service and fetch the key. So once the key is available, the Cloud HSM returns the key material to that helper process, and then the helper process returns the response back to the kernel saying, I have the key material now, and it instantiates the key, and the kernel just returns a proper error code to the application indicating that the key is available to use. So, and the advantage of request key is basically it provides a centralized operating system API to request keys for applications. And so you as an application developer do not have to worry about KMS or HSM's URIs. You do not have to add code to your application to be able to talk to Vault or anything. The only thing you have to do is call one function, request key, and the operating system should give it to you, right? So you kind of fully decouple your applications from your key store backends in this way. And it's basically a more secure way to instantiate the application because your application never touches any plain text or even encrypted cryptographic material. All it does, it asks the kernel to provide you the key, and the kernel basically does it for you. Yeah, so the idea is that with request key, the support of and key management becomes your core feature of the operating system itself, where it should be, right? And not everyone should code their own stuff. As an example here, what I wanted to show you how convenient it is, and basically with what I decided to implement a proof of concept. So instead of fetching keys from Cloud HSM so you can try it at home, I wrote a small plugin for the request key to actually make the TPM to provision application-specific keys for your system. So these keys will be unique to every application, and they will be also cryptographically bound to your TPM. So like different machines will still have different keys because everyone's TPM is different. Yeah, you can check the link today. I'm really sorry. Basically, it's just a simple proof of concept, so I used Python to write this plugin and not a real programming language. So, but it kind of illustrates the point here. Yeah, and the nice thing about it, because you can write plugins in any programming languages. It could be, even though the whole helper process is written in C, you can write plugins in Python, Go, Java, JavaScript, and whatever you want. Yeah, so if you download my plugin, don't bother too much about it. This is how you configure it. So you can read the documentation later, what that means. But the TLDR here is when an application requests a key with identifier which starts with TPM2, I should call my plugin to actually fetch that key, right? And that plugin has actually two modes. So this is how I provision unique keys. So the first, it has two parameters. The first one is 32 is the key length. So for example, hey, I want, and this application requests a key which is 32 bytes. And the unique factor it requests to be used is the application path. So like different application, depending on their path in the file system, will get different keys. So as you can see, I requested the key through my plugin. I got some key back. So you see the serial number. It's a user key, so I can read it back. So if I read it, I can see some bytes. And if you reproduce it, your bytes will be obviously different because you have a different TPM. But what I can do now, I can remove that key, delete it securely, and I can re-request it again with the same parameter. So now you see the serial number is different. So it's a different kernel object was recreated. But if you read it back, you get the same byte. So like, because this key, my plugin ensures that this key is unique for that application. And again, we can delete it, and we can actually make sure it works. So now what I can do is I can move my application from one path, from user bin directory to my home directory. So I'm changing the file system path, and I'm re-requesting the same key. But now I get different bytes back because my executable is placed in a different position in the file system. So for example, imagine you would use this to provision a static SSH server key. So whatever is at user has been SSHD will get that key. But no other application can get the same key because they are located in a different file system. Pass. Yeah, and also what I wanted to show here, it also takes user ID into the account. So if I rerun the same thing, even it's within the same path, if I rerun it with a different user, so for example, like as a super user, I'll get a different key now because different users should have different keys, right? The another nice mode is instead of the path, you can use an application code checksum as an identification factor. So now the generated key will be unique to your system and to the binary code that is requesting that key. So, for example, I can request the key. I can delete it again. Now I'm moving my application from one path to another, but I can now see that the key is the same because the key is cryptographically bound to the application code. And as long as the binary is the same, you get the same key, right? And to show it actually works, now I'm going to do some hackery stuff, and I'm going to patch my executable. So I know the keyctl utility has an error message called error string called bad message. So I'll patch it and switch it to bad massage. I'm changing 1 byte in the code, but it will still work because it's just an error string. And if I reuse that application, I will now getting a different key because even 1 byte change force my application code to change, and I'm getting a different unique key for the application. Cool. This is mostly what I want to say today. I think the slides will be distributed later, but here are some useful links for the reading. So the first 3 or 4 even is documentation for the Linux kernel keystore. Everything that I presented today and more is described in the Cloudflare blog post, with all these examples I presented today also available there, so you can reread it back, copy-paste all the code examples, and try to play with them yourself. Thank you very much. And I don't know if we have time for questions or not. If we don't, otherwise I'll be downstairs at the speaker's corner, so you can reach me and ask me questions. Thank you.
Questions? Do you have some questions? Raise a hand and I'll come to you with the microphone. Okay, we have a question.
Hi, thanks for the great presentation. I just wonder, you mentioned that the key is bound to the checksum of the binary that you execute. Mm-hmm. I just wonder what will happen after update. Probably this checksum will change. So this should change the signature.
Yeah, this is a good question, and this is why I implemented the second, the path-based approach. So actually, to think about that. So for example, if you run your SSH server, right, and you have a unique key, you obviously want to support updates, right? So like when the new SSH server is installed, you don't want the key to change. So like this is why you probably should use the path approach for SSH, but there are some use cases where you want to have like strict integrity of your keys. So like
it's a more secure approach,
like,
even more.
Say a fixed image. So yeah, you can use both. So like, and probably more.
Okay, thanks.
Is there other question? Let's see your raised hands.
Ima.
6 more minutes for questions if you want.
Ima question.
Hello.
You can,
sorry if the question is off.
Where is the questionnaire? The question
Here on the left. Yeah. So question is, in the first example that you showed, you have the code that is using some secret key, and then you have another bug that, like in the logs, which, while causing exception, spits out the secret key and makes it available to snatch, basically. So what all your explanations did is move that secret key to the kernel. Yeah.
I can't really understand.
What?
Maybe can you come closer?
Or speak louder, please.
Yeah, I can try speaking louder. Okay. So, in your explanations, you said that you can basically exploit the secret key being available in the code with the logs.
Yes.
If there's an error in the logs, it will spit out the secret key and make it available to being snatched. So what your tool does is moving that secret to the kernel, so it's not being available in the code anymore. And then use the code to access the kernel to get that secret key. What happens if you have the same error in the logs and you access the secret key, you get it from the kernel, and you use it to perform some operation in the code, but then the logs cause that same error and try to spit out the secret key again?
Okay, I mean, this is a good question, and we talked about, like, I'm mostly talking about keys, but we can have two types of, one is secret. Secret can be a password and an API token or something else, and an actual cryptographic key. So this is much more useful for cryptographic keys, because you rightfully mentioned that if I want to use an API token, I need to get it out and send it somewhere, right, in my HTTP request. Whereas the advantage, if you do have a cryptographic key, you don't have to get it out. As we see an example with an RSA key, but you can also do a symmetric key. You don't have to get the key back. You can perform cryptographic operations based on the key without reading the key. So you can say, like, instead of reading the key, you can say, hey, kernel, encrypt this data structure with the key you have, and the kernel will do it, but you don't have to read the key. But even with secrets, it's still kind of useful in the sense that you're still limiting the window when the key is available in the application address space. And moreover, it's very useful for, like, garbage collected languages, so you cannot easily, like, zero out the memory when you don't need the key, or when your application crashes. So if they store there, the kernel is responsible for securely deleting them from the memory.
So, if I understood it correctly, in that same case with the log exception, the key will be available and will be in that error message.
Yes,
but before that and after that, it won't be stored in the memory unless you store it in a variable.
Yes.
Okay, thank you.
Thank you. Is there another question? We have 2 more minutes and a half. If you can't think of a question now, you can, of course, meet Ignat in the speaker's corner during the next break. Questions? No? So let's send him off of the stage with a big round of applause, Ignat Korchagin!